Alright, so I thought this would be a great problem for me to review because it covers a lot of the topics that were suggested by you. So we have, almost looks like a roller coaster, but small block of mass 2m sits at rest on the bottom of the circular. Always is good to note when something's circular. Vertical loop shown above, which has radius r, and it is frictionless. And here we have a collision, and the bullet of mass m strikes the block horizontally and remains embedded. So we have an inelastic collision here, which is important for us to note. So we want to determine all of the following in terms of m, v naught, r, and g. So right away, if we're starting, part A I'll do up here. If we're starting with an inelastic collision, we always start with P before equals P after. Apologize for the bad handwriting. And initially, since this block is at rest, we can just ignore it. It has no momentum before the collision. So all of the momentum is in this bullet. And remember, momentum equals m times v. This marker would write. Guess I can't write up there. So we have mv, and then afterwards we have some final velocity, which is what we're looking for, and then it's an inelastic collision, so we're going to add up m plus m, and now let's plug in. So we have a bullet of mass m times v naught equals this final velocity we're looking for. The bullet has a mass of m, and the block has a mass of 2m. So that becomes 3m. So for our speed, we should get m times v naught over 3m equals vf. We can cancel these m's. So we should get vf equals v naught over 3. And there's part A. Now let's go on to part B. So what are we looking for here? The kinetic energy of the block and bullet when they reach point P on the loop. Okay, so when we reach point P, it's important to note that that's halfway up. Well, it tells us here. So the height is going to be r. And if we think about at the very bottom of the loop, it has no height. So at the very bottom, it's going to be all kinetic. And then as it transfers energy from kinetic to potential, at point P, we're going to have both kinetic and potential. So again, for part B, we could do EI equals EF, where initially it's all kinetic. And then at point P, let's call it, I don't know, the kinetic at point P plus the potential at point P. And we just found the speed. So when we plug in here, and we can actually, I was going to plug in 1/2 mv squared, but since we're looking for the kinetic, we can just leave this as kp plus mgh. Now let's plug in, we'll move it over, and we'll get our expression. Here we have 1/2 times 3m times v naught over 3 squared equals this kinetic plus, let's see, we have mass 3m. Okay, leave it as g. And the height is r. So let's multiply this one out. So we have 1 over 2 times 3m v naught squared all over 9, 3 squared is 9, equals Kp plus 3m gr. Subtract it over, so let's clean this up. 3 over 18 would reduce to 1/6. So I'm going to subtract this over. So I should get 1/6 mv naught squared minus 3mgr equals Kp. And there is my on to part C, where we're looking for the minimum speed of the block at the top of the loop to remain in contact with the track at all times. So quickly, free body diagram at this point. Force of gravity, definitely pointing downwards. And the normal force is always also pointing downwards at this point because it's towards the center of the circle. And we can do sum of the forces. And when we're talking about centripetal force, it's always with respect to the radius. So in this case, we would have force of gravity plus the normal force equals mv squared over r. Now, the minimum speed for it to remain in contact, if we think about that, if we're going very slowly, or if we're going too slow, we would fall down and we wouldn't make it across the loop. So in that case, the minimum speed for it to remain in contact with the track, the normal force will go to 0. So I can plug in for a force of gravity, mg equals mv squared over r. And whether you plug in 3m or just cancel the m's now, we get this. So we'll rearrange the front problem. We get rg equals v squared. So v, or the v min, is equal to the square root of rg. And there we have it. The last two parts of this problem, we have the new required entry speed, v naught of the block, and the bullet at the bottom of the loop, such that the conditions in part C apply. So now basically what we're going to do is energy conservation from the top of the loop to the bottom. So I'm going to do conservation of energy. Now, here we're going to start at the top. This is an I. We're going to start at the top and figure out what the speed at the bottom is. So at the top of the loop, we definitely have potential at the top. So we'll call it potential at the top plus kinetic at the top because it is moving equals, there's no potential at the bottom, so call it KB, kinetic at the bottom. Now we can plug in. So we got mgh plus 1/2 mvt squared equals 1/2 mv bottom squared. Now, if it's helpful, all of these have an m in it. We get rid of these. And now let's plug in specific values. So g at the top, remember that's the diameter, so it's going to be 2r plus 1/2. Here is from part C. If we remember, we found it's the square root of rg. Equals 1/2 times, this VB is what we're looking for. So here we get 2 rg plus rg squared is just rg equals 1/2 VB squared. So here we get 2.5 Rg Vb squared, multiply both sides by 2, 5 Rg equals Vb squared. So Vb is equal to square root 5 Rg. And then let's finish this problem up. The new initial speed of the bullet to produce the speed from part D above. So now we're basically going back to part A, and we want to do this same thing. But remember, if this is the speed at the bottom of the ramp, that is, if I go back to part A, that is basically the final velocity after the collision. So for part E, we're going to go back to conservation of momentum. Now what we're looking for is we're basically looking for the new V naught. So let's call it M. I don't want to use B because that's bullet. Let's say V naught prime equals. Now we have the final velocity. So I'll just do it up here. Vf and m plus 2m. But here our final velocity is the square root of 5 Rg times the mass, which is 3m. So then I can get rid of these m's. So V naught prime is equal to 3 times the square root of 5 Rg. And there we have it.